Hello everyone, this is Dr. Shivam Singh working as an assistant professor in the Department of Electronics and Communication Engineering, ABES Engineering College, Ghaziabad. And today I'm going to deliver a lecture on Introduction to Signal. Basically, it is the part of signals and system, and I have picked signal part. Now moving to outline. So that includes introduction, elementary signals, operations on signals, classification of signals, applications, and references. Now, starting with the introduction. So, the basic definition, a signal is the function of one or more independent variables that carries some information to represent a physical phenomena. You can better understand with the help of this diagram shown here. So here the information is given in terms of amplitude. You can see f of t is the amplitude and t is the time. So signal with its amplitude is varying with respect to time. Means as the time changes, the amplitude also changes. Amplitude in terms of volts. You can see. Now elementary signals talking about. So there are mainly two types of elementary signals that you can see often. So this type of signal you will use in your most of the calculations. First one is sinusoidal, second one is exponential signal. So in diagram first, you can see the nature of sinusoidal signal. You can see the positive half cycle, negative half cycle, and it continues like that. So such signals are called sinusoidal waves. And in the second diagram, you can see exponentially increasing signal and exponentially decreasing signal. So that increasing and decreasing depends on the value of this small a. So if the value of small a is positive, then the function will increase exponentially. And if it is negative, then the function will decrease exponentially. Now the basic mathematical expression for these two signals, that is sinusoidal and exponential. So x of t equal to a sine 2 pi f naught c. So to be more specific, you can see here, let me denote it. So you can see here capital A, you can see the amplitude here, small f naught, that is frequency of the signal, and theta is the phase shift. So this is the general mathematical expression for the sinusoidal signal. Now the same for the exponential signal, you can see it's capital A, the amplitude of the signal, and this is small a, as I have discussed in the previous slide, that the nature of the exponential signal, whether it is increasing or decreasing, will depend on the signed magnitude of this a. Okay. Now moving ahead. So you can see the types of elementary signals. So the first type is unit step signal. So the basic mathematical expression for unit step signal, you can see here. U of t equal to 1 for t greater than 0 and u of t equal to 0 for t less than 0. So let me denote it first. See here. For t greater than 0, here you can see the diagram. For t greater than 0, the value is 1. And for t less than 0, the value is 0. So you can represent this type of signal with the help of graph also. So moving ahead. Now signum function. So signum function is also a type of elementary signal. You can see the basic mathematical expression for signum function is signum of t equal to 1 for t greater than 0. 0 at t equal to 0 and minus 1 at t less than 0. And if you want, you can also express the signum t function in terms of unit step function, which I have discussed earlier. 2u of t minus 1 means it is equivalent to 2u of t minus 1. And the figure for this mathematical expression, you can see signum t. This is 1 for t greater than 0, 0 at t equal to 0, and minus 1 at t less than 0. Now unit ramp function. So you can see the basic mathematical equation for unit ramp function is also for t greater than 0, it is t. T means what? A slope. And here what is the slope value? Simple, it is 1. Means it is the increasing function for t greater than 0 with a slope 1. See here, with slope 1, it is increasing. And in the first point, you can see it is the integral form of the unit step function. Means if you want, you can also get the same function if you integrate the unit step function. You can see here also. If you integrate, let me denote it first here, just a second. And if I want to denote, then see the integration of that unit step function will give you unit ramp function. So in this way, you can express unit ramp function. Now properties, now moving to unit impulse function or unit impulse signal. So it is the derivative form of the unit step function. Means if you differentiate unit step function, then you can get the unit impulse function. And the mathematical definition for the unit impulse function is that integration of A will vary from minus infinite to and B will vary to in plus infinite. So if you want, I can also show you, just a second. So here you can see this A will vary from minus infinite and this B to plus infinite. So this is the range of A and B. So if you integrate this range unit impulse function between this range, then you'll get 1 and 0 otherwise. So in this way, you can get the unit impulse function. If you want, you can also see the graphical representation of the unit impulse function. Here you can see the basic diagram of G dash of t I have defined between minus a by 2 to a by 2. When you compress this signal, see here the red arrow is denoting that the signal is compressing from both sides. Then if you will compress, then at origin you will get a signal like this with area 1 at 0. Means it will exist only at t equal to 0. Otherwise, you will get 0 value for all the other values of t. Now, properties of unit impulse function, then time shifting property means you can apply unit impulse function to the different form of the signals. So here you can see summation integration of a to b del of t minus lambda dt equal to 1. Here in the previous slide, you have seen that this one will be there at t equal to 0. Now you have shifted the signal at t equal to lambda. So the same one you will get at t equal to lambda. Here I have denoted in the red arrow. Now at lambda you will get 1, area 1. While in the previous you can see, if I show you, in previous you will get 1 at t equal to 0. Now due to the shifting of lambda, you will get the same value 1 at t equal to lambda. Second one is time sampling property. So time sampling property says integration of minus infinite to infinite g of t, a function. If you multiply some delta function with a time delay of t naught, then you'll get the function value by putting t naught in the original function g of t. Now operations of signals. So you can apply different operations on a signal, that is time shifting, time scaling, time inversion, or time folding. So starting with the first, time shifting. So here x of t is given, the original signal. Let me denote it first. So here you can see this x of t is given, the original signal is given. Now if you want to shift this signal towards right of this t or left of this t or time axis, then you can. Here in the second graph, you can see the signal is shifted by amount of t naught towards right. So in this way, you can use this time shifting property to operate your signal either towards right, left, or origin. So moving towards another property, time scaling. So time scaling for the given function x of t, x of at is the time scaled version of x of t. Here a denotes the value, means if you can see in these 2 points, then for a greater than 1, period of function x of t reduces and function speeds up. And for a less than 1, the period of x of t increases and the function shows down. You can better understand with the help of graph. Let me show you. Here you can see. So let me denote it first, then we'll see. So given x of t, here x of t is original signal. Now what they are saying, we are to find y of t equal to x of 2t. Here a will be 2. So what you have seen in the previous slide, that if a is greater than 1, then your signal will be compressed in time domain. Here you can see this is the time domain or time axis. Compressed means what? Here you can see the original signal. Now it will be compressed in time domain. See here, from left side and from right side, it is compressed. So this is the scaling property that you can use. Okay. So now moving ahead. Now time reversal property. So time reversal says if original signal is given x of t, and if you want to get x of minus t, then you can take the mirror image. See here, mirror image. Here original signal x of t is given, and if you want to find out x of minus t, then you can take the mirror image of this original signal. See, the second graph is the graph of x of minus t. So in this way, you can apply time reversal property also in most of the problem where it is required to solve. Now classification of signals. So here it is given, signal can be classified in these different types: deterministic and non-deterministic signals, periodic and aperiodic signals, even and odd signals, energy and power signals. We will see one by one. So deterministic and non-deterministic signal, if we are talking about, then first deterministic signal, then behavior of such signals is predictive with respect to time. Means what? Means you'll get the exact value at a particular time. See here, it is defined. If you see the diagram, let me denote it. Then you will see here. Just a second. So here you will see the sinusoidal waveform. As I told you, this is sinusoidal waveform. This is sinusoidal waveform. So you'll see for each and every time instant, the value is defined. For each and every time instant, the value is defined. So such type of signals are called deterministic signal. Here it is given, you can see here. There is no uncertainty with respect to its value at any time. Means what? Means you will get value at each and every time instant. For example, I have taken x of t equal to sine t. I told you the nature of sine t waveform or sine waveform. So you will see positive half, negative half, and it is limited. Means it is ranging between -1 to 1, and the value for such type of signal is defined for each and every time instant, whether it is 0, 1, 2, 3, up to 10, 20, like that. Now moving ahead, non-deterministic or random signal. So behavior of these signals is random, not predictable with respect to time. Yes, means you cannot predict the exact value of the signal for each and every time instant. So that's why it is non-deterministic signal. For example, I have shown thermal noise. Means noise is also a type of signal. Means whatever you are speaking, it is also a kind of wave or vibration. So the pattern of vibration you cannot predict. So that's why it is said random signal or non-deterministic signal. Now moving to the second type, classification of signals. The second classification, periodic and non-periodic signals. So for periodic signal, what it is written, xt is said to be periodic if it follows the given condition. What is the condition? Means if you have signal x of t, okay, and if it is equal to x of t plus capital T naught. What does it mean? Means this is capital T naught is the period of the signal. Means if you put the period of the signal in the place of t, if you'll put or you'll add the period of the signal t naught in the original signal, and if you'll still get x of t, then we can say that the signal is periodic with the time period of t naught. Here is the mathematical expression, x of t a cos omega t, okay, and now I'm replacing x of t plus t naught in the expression. So if you'll get the same A cos omega t, then you can say that the signal is periodic. Non-periodic signals, the same. If you'll put t plus t naught in the place of t, and you'll not get the exact original signal x of t, then we can say that the signal is not periodic. Or we can see a not periodic signal is assumed to have a period t equal to infinite, means you cannot define the period. Now moving to even and odd signals. So what does it mean? For even function, your function is defined g of t, and if in the place of t, if you'll put minus t, then if both equal, then you can say a function is even. Now on the contrary, for odd functions, g of t, it is given, and if you'll put minus t in the place of t, then you'll get minus of g of minus t. When such condition happens, then it will be the odd function. So this is the basic difference between even and odd signals. Now, if you want to find out the even part and odd part of a given signal, suppose g of t, you can better understand with the help of notation also. See here. Just a second. So see here. Suppose a function is given. Just a second. So here, the previous slide, you can see the even part and odd part. Suppose I am denoting this with see here, g of t. G of t is original signal. Okay, and g of t will be the combination of ge of t and go of t. Get means even part of gt. Got means odd part of gt. So if you want to find out the even and odd part of a given signal g of t, then what you need to do, here you can see g of t plus g of minus t divided by 2. If you put g of t, then g of minus t, and you'll divide by 2, then you'll get the even part of the signal given g of t. And if you want to find out odd part, then g of t minus of g of minus t divided by 2. In this way, you can get the odd part of the signal. So you can get even and odd part of a given signal g of t with the help of this formula given. Now, energy and power signals. So we can define energy, we can define signal in two ways, whether it is energy signal or power signal. So here's a condition given: a signal with finite energy and zero power is called energy signal, while the condition goes like this. If you talk about a energy signal, then it will be ranged between 0 to infinite. And if the signal is energy signal, then the power of such signal will be 0. And if you want to find out the amount of energy, then you can find out with the help of given formula. So, integration of minus infinite to plus infinite. This is x of t is a function given. Then if you take the mod and square it and integrate it, then you will get the exact energy of the signal. Likewise, if you want to calculate power, then you can calculate power with the help of this expression given. First of all, the condition goes like this: if a signal is a power signal, then the power will be ranged between 0 to infinite, and energy of a power signal will be infinite always. And if you want to calculate, then you can always calculate average power. So it will be calculated with the help of the formula given: 1 by t. T is the period of the signal, and the limit goes like minus t by 2 to t by 2. The same x of t function, then you can take mod square. In this way, you can get the average power of the signal. Now moving towards the applications, then you can employ lots of applications are there of the signals. Few applications are there. You can use different type of signals to send your information from one end to another end. So in this way, you can use signals for the communication purpose, and sometimes you can use signals in image processing, in video processing, and you can also use signals for seismic data processing. These are the references that I have used for the content preparation. Thank you so much for your patience.